So until the last day when we were studying machines, we completed up to the classification of the three class of levers. So we discussed about the basic ideas of what are these mechanical advantage, velocity ratio or efficiency, what do these terms mean. Then what is the difference between an ideal machine and a machine in reality, a real life. And finally, what are levers, what are their classifications and the corresponding examples of those levers. Today we will be discussing about another simple machine, that is pulley. Now, as we said, the lever is also a simple machine and pulley is a second type of simple machines. So what do we have in a pulley? What is basically a pulley? You might have seen it in various pictures or in various kind of videos, that there is some kind of structure like this which is called rigid support. From there onto a frame generally made of wood, you see something like this which looks much like a wheel, and on two ends of that wheel there are two strings. On one end there is some person pulling down the string, and on the other end generally there is a bucket, because pulley finds application in various kind of wells in villages to lift water. So they put allow the string to loosen, the bucket goes down into the well, it brings up water, and then from this end, the free end of the string, when someone pulls down on the string, the bucket again comes up. So this is a general application of pulley which you might be familiar with. How does a pulley look like? What is its basic structure? So first of all, if you look at a pulley, obviously there is always something like this, a rigid support onto which the entire structure of the pulley is attached. So with this rigid support there is a hook, and to that hook you shall find that there is kind of a frame like this, through which the axle passes. From the center of this, the axle of the pulley passes, and around this axle, around this frame, there is this wheel like structure. As I said, this is known as the disc of the pulley, and this disc of the pulley has got a grooved rim. So this outer structure, this one is called the grooved rim. Rim means the boundary, and grooved means there's a hollow structure within it, like there's kind of a tunnel inside this rim through which the string can pass, and it is held on to this wooden frame in the center, to this block, this axle, with this kind of attachment, and through this grooved rim passes the strings of the pulley, with which we can either attach the load or apply the effort. But generally when we will draw the pulley, we will simply draw this circle, we won't draw the exact technical details each time. So this is how a pulley generally looks like. Now what do we have here in our syllabus? The first thing we need to study about is the single fixed pulley. Single fixed pulley. As you can see from the name, you can get an idea about it, what kind of pulley it is. First of all, it is single. That means there is only one pulley. We will study consequently as we go that there are pulleys where there are a combination of more than one pulley. And fixed. Fixed means this axle, or through which the axis of rotation passes, that is fixed in space. So what does a single fixed pulley look like? It looks something like this. There's a rigid support, as I said before. Onto the rigid support is attached a hook. With the hook you find the block, the frame, and to this you will find that the pulley is attached. And as I said, this is the grooved rim, on 2 edges of which are the strings. On one edge any person applies the effort E, and at the other end we have got the load which we want to raise, the load L. Now there will be certain assumptions when we study pulley. You shall find it in your book as well, that whenever we are studying or dealing with ideal machines, we shall assume that there is no friction in the parts of the machine, and that this string that which we are using, these strings are massless, or you can say of negligible mass, and they are moving through a grooved rim which is frictionless, and that the string is inextensible. So this is the assumption that we made before we move into the domain of an ideal pulley. Now this part that I labeled just now as T, these are the tension, the force of tension developing in the string, and they always develop in the direction opposite to that of the effort and the load, that is in the upward direction in this case. So if you look into this part of the string for equilibrium, the effort is equal to tension, and if you look into this part of the string, again for equilibrium, the load is equal to tension. Now what is our mechanical advantage? We studied mechanical advantage is load divided by effort. So for this case it's tension divided by tension, which is 1. Since mechanical advantage is 1, what can we infer from that? Now we again discuss this, that if mechanical advantage is greater than 1, it acts as a force multiplier, and if it is less than 1, it will act as a speed multiplier. And since here mechanical advantage is equal to 1, a single fixed pulley is used for the purpose of changing the direction of effort to our convenience. So when we studied the basic idea of machine, we discussed this, that a machine can either help us to lift a heavy load by applying a less effort. Machines can also help us by allowing us to gain speed, like we make a smaller movement of the effort and the load moves a greater distance. And finally the machine can help us to change the direction of our effort to a convenient one. Now in the case of the single fixed pulley, this particular case comes into play, changing the direction of effort to a convenient one. How? Well, if the pulley wasn't here and you were suppose you are trying to lifting this load up, what you would have to do is you would have to apply the effort in the upward direction, that is against the gravity. This is the downward direction, so gravity is acting in this direction, so you would have to apply your effort in the upward direction, in the direction of gravity, against the gravity. But since you have the pulley, now you can apply your effort in the downward direction, that is along the direction of gravity. So if you are a person standing here holding this string, then simply by pulling on the string you can make the load go up, and for this purpose you can use your own body weight, because we know our weight, which is equal to m times g, acts in the downward direction. So our own weight can be this effort. So this is the advantage of using a single fixed pulley. So if you are asked this question that why do we use a single fixed pulley although we are not getting a case of force multiplication or speed multiplication, this is the reason. We change the direction of the force applied, that is our effort, to such a convenient direction that we can use our own body weight as the effort. That's the reason for using the single fixed pulley. But there might be certain times when you would like to have a gain in force, that is a force multiplier, when you are lifting quite a heavy load that even your own weight is not enough. So for those kind of situations, what we shall be using is known as a single movable pulley. So single movable pulley helps us in acting as a force multiplier to have a gain in the force, that is it has a mechanical advantage which is greater than 1. How does it look like, the basic structure? Well, again we have this kind of a rigid support, but this time at the rigid support we don't have the frame of the pulley attached, rather we have one end of the string attached, and the pulley lies somewhere here below, and this other end, this is the free end where we apply our effort. So now this point of the pulley, which is the point through which the axis of rotation passes, that point of the pulley is movable, it is no longer fixed, and here you have the block. With that block you attach the load that you are trying to lift. So what is the difference between the single movable and single fixed pulley? In the single fixed pulley, the load was attached to one end of the string. In single movable pulley, load is attached to the block. In single fixed pulley, we had to apply effort in downward direction. Here we will have to apply effort in upward direction. And finally, in single fixed pulley, the block or the frame was fixed in place, and in the single movable pulley, the block or frame is movable, as is the axis of rotation, and the load is attached to the block. Now when you apply an effort in the upward direction, this entire system moves up, or similarly if you allow it to fall, the entire system moves down, and this part of the string remains fixed in place. As before, tensions shall be acting in the strings, and as I said, always in the upward direction. They always act in direction opposite to that of the load, so they will be acting in the upward direction. So now if we are to write load and effort in terms of tension, well, effort is simply tension, because effort is this tension here, that is effort. But what is load? The load in the downward direction, that is this one, is balanced by two forces in the upward direction, the two tensions in two parts of the string. If you just draw the diagram of the forces, load acting in downward direction is balanced by tension acting in both the parts of the strings. So load is 2 times tension. So now if we are asked to find out mechanical advantage, it is load by effort, which is 2 times tension divided by tension, which is 2. A mechanical advantage greater than 1 implies that we can use a single movable pulley as a force multiplier. If you go on to find the velocity ratio of this, you will find velocity ratio is displacement of effort by displacement of load. Now displacement of effort in this case is this portion. So in order to make the load move up through a distance d, you shall have to move the effort through a distance 2d. This is obvious because for every say 1 centimeter movement of the load in the upward direction, this portion of the string should move 1 centimeter up, and this portion of the string should move 1 centimeter up. Only when this entire system moves 1 centimeter up will the lower part of the load also move 1 centimeter up. Thus we see that for every 1 centimeter upward movement of load, the efforts here move by a distance of 2 centimeter. So similarly, if we take any random variable d, the movement of effort will be 2 times d. Putting that into place, we get velocity ratio is also 2. And from here we know that eta, which is the mechanical advantage by velocity ratio, also known as efficiency, is therefore 2 by 2, that's 1, or in terms of percent it is 100%. That is the value of efficiency of a single movable pulley, again, which is ideal, because we know that for an ideal pulley the string is massless, it is inextensible, perfectly elastic, then there are no frictions in any part of the pulley. But in real cases, none of this is possible. A string cannot be massless, it has got some finite mass. Similarly, parts cannot be perfectly frictionless. There is, even if it is negligible, there is some friction. The strings are never perfectly elastic or perfectly inextensible. So for these reasons, the eta, value of efficiency, for a real single movable pulley is always less than that of 100%. So now we have the basic idea of a single fixed pulley and a single movable pulley. Now we see each of this has got a set of advantage and a set of disadvantage. Single fixed pulley has the advantage, and that is we can simply use our body weight to pull down on the load. The direction of effort is very convenient. But again, the disadvantage is we don't get a multiplication in force. In single movable pulley, the multiplication of force is there. That is, by applying a force of 1 Newton, you can lift a load of 2 Newton. It provides a 2 times multiplication. But now the disadvantage is that you have to apply the effort against gravity in the upward direction. So, in order to get the best of both the cases and to nullify their disadvantages, what we can do is we can use a combination of a single fixed and single movable pulley. combination of single fixed and movable pulley, how shall it look like? Well, once again, you will have this rigid support on the top portion. First, to the left, you will draw the single movable pulley. To the hook will be attached one end of the string. There shall be the pulley here, and attached with the frame or block of that pulley you will have the load somewhere here. But now the free end of the string at which you were applying the effort, there you shall pass it through another pulley, which is a single fixed pulley. This pulley has got its axis of rotation moving, but this pulley is fixed here, so its axis of rotation is fixed in place. And now this string, which is passing like this, comes down again, and simply by applying the effort here, you can make the load move up. Tension, as always, acting opposite to load in the upward direction. These are my two pulleys. So this is pulley A and this is pulley B. Pulley A is a movable pulley, B is a fixed pulley. And as you can see, now since I am using the movable pulley, I am getting the mechanical advantage of 2. So by applying an effort of 10 Newton, I can lift a load of 20 Newtons. And at the same time, by virtue of using the fixed pulley, I can change the direction to convenient one. If you have this question like, because I am using two pulleys, will the mechanical advantage change? Well, the answer is no, because the fixed pulley does not affect mechanical advantage or velocity ratio in any manner, because it has a value 1. So whatever is the value of mechanical advantage or velocity ratio for the movable pulley, that remains as well. So you get the best of both the cases. So this is the reason why for using a movable and a fixed pulley together, you are getting the force multiplier case, you are also getting the convenient direction case. And basically, if you are asked to draw the diagram, not only for this one but any of these pulleys, as I always said, diagrams ought to be drawn with a pencil. So draw that, properly label the direction of forces, load and effort acting in the downward direction and the tensions acting in the upward directions, and finally label as to whether it's a fixed pulley, movable pulley, or a combination of both.